Heat transfer, chapter 1, lecture 3. In this lecture, we'll talk about conduction. So we can look at an equation we had before, and we can imagine the case where, uh, when the delta x goes to 0, and so in that case, you end up, instead of having a delta t over delta x, you end up with a derivative dt over dx. So this is what's known as Fourier's law of heat conduction. K is the constant, is the thermal conductivity. It's the measure of the ability of the material to conduct heat, and so some materials are much better at that than others. So let's explain the negative sign here. So since heat is conducted in the direction of decreasing temperature, in other words, from hot to cold, the temperature gradient becomes negative when the temperature decreases with increasing x. So this negative sign ensures that the heat transfer uh, is in the positive direction, is a positive quantity, if that sort of makes sense, like the diagram we have here. So here's an analysis of heat conduction. A represents what's known as the cross-sectional area. It's the normal area normal to the direction of the heat flow. So for the wall, it's just the height times the width. So again, let's take a look at another example of this. And this is, the best way to learn these equations is to look at problems. So here we have, we want to calculate the cost of heat loss through a roof. So here we have a kind of a flat house. We have a rectangular roof that it's 6 meters by 8 meters. It's made out of concrete. It's 0.25 meters thick, and it's on the outside is 4 degrees C. On the inside, in the inside of the house, it's 15 degrees C. So here we're going to use the Fourier heat conduction equation. So the value for K, we're going to have to look that up, and so he tells us that for concrete it's 0.8 watts per meter Kelvin, and so we want to calculate it. So he says it's 15 degrees C and 4 degrees C, for 10 hours, right? So we want to determine the rate of heat loss for part A, and for part B, we want to determine how much it's going to cost us, how much energy do we lose in cost. So K, we're given that the area we can find, that's 8 meters by 6 meters, so it's 48 square meters. Delta T, 15 minus 4, and the width here, that's the L, is 0.25. So let me point that out. Now you have to kind of be careful with this. L, you might think this is length, but it's actually the thickness. So the heat is being transferred perpendicular, right? Up this way. So that's in the direction of L. So L is 0.25 here. So you can calculate that. It's 1.69 kilowatts. So that was part A. So for part B, we want to calculate the amount of heat. So it's the heat flux, which is 1.69 kilowatts times 10 hours. So that's 16.9 kilowatt hours, and the unit cost is 8 cents a kilowatt hour. So you can multiply that by the kilowatts, and you get about 1.3, about $1.35. So some of the thermal conductivities, these are a table of some materials at room temperature. So you can see what the values here are for different materials. These are some other kind of shows you another. He gives another table to show you some different the range of thermal conductivities for various materials at room temperature. Uh, so nothing unusual here. You can see it goes up, of course, with the hardness, right? So he also gives us a couple more graphs. This one is a plot of K versus temperature. You can see the different graphs here. Here's another table he gives us here. Okay, so that's the end of this lecture on conduction. The next lecture we'll take a look at brief introduction to convection and radiation.